Woo! Alright, so we're going to start talking about concavity. Second derivative test will be for sure tomorrow. I didn't want to put it all in one day. And I forgot to change titles. So, just concavity today. So here's your definition. Pause video so that way you can get it written down. Honestly, the best thing for this definition was to look at it pictorially or get a picture definition. So that's what we're going to talk about this part. So if I'm going downward or I have a curve down, we're going to say it's concave down. And if my curve is kind of going up, we're going to say it's concave up. So it's similar to increasing and decreasing. It's just taking a look at something dealing with a different derivative. So, that being said, woohoo, test for concavity. So first things first. Now, notice that is double prime of x. Same thing here. Go back. This is also double prime of x. So that means that we are taking the what derivative? What? That's our second derivative. Okay, keeping that in mind. Write down that bad boy. So essentially what that definition is saying is that, say I have some random crazy graph and it looks like this. That point of inflection is where it would change from going concave up to concave down, or in that case, left to right. So those points right there would be that point of inflection. So if I go back for a second and we look here at this nice green dot, that green dot is that point of inflection or an inflection point. So that's what those things are saying, is that they exist. And then this next one is talking about what it is, kind of where it is. And then now we're going to go ahead and solve it. And we're going to show it mathematically. So now that we've talked about, well, we've looked at the different ways of doing it, let's talk about how we're going to solve it. So first things first is we're going to take the first derivative, because in order to get to the second derivative, I need to get to the first derivative. So the first derivative of this guy is going to be 3, what am I doing? It's going to be 4x cubed minus 12x squared. Then I'm going to go ahead and take the second derivative because we're dealing with the second derivative today. So that's going to give me 12x squared minus 24x. Kind of like when we dealt with our first derivative test, what we're going to do is we're going to set this now equal to 0. And we're going to solve for x again. So I take out an x. I'm going to take out a 12x, excuse me. I'm left with x minus 2. So my two x value points here are 0 and 2. Now I want to figure out where those points are, so I'm just going to go ahead and plug them in to the original function. So when I plug in 0 to the original function, I have 0 minus 0, which is still 0. Now, my 2, however, is going to be a different story. So I have 2 to the 4th, which is 16, minus 2 to the 3rd, which is 8. 8 times 4 is 32. So I have 16 minus 32, which gives me a negative 16. So that point is at 2, negative 16. So I have those 2 different points. Now I need to discover what's going to go on with my graph. Am I going to concave up or am I going to concave down? So my 2 points of inflection, I'm trying to pick a different color here, were 0 and 2. So just like with my first part, I had my 0. 0 is less than x is less than 2 and 2. So my test spots. So same idea. We picked a value that was less than 0, so say negative 1. Now, instead of plugging it into the first derivative, I'm going to plug in that negative 1 into the second derivative. I'm going to leave that little spot there so it keeps in your mind that you know we're plugging it in. And just like with the first derivative test, we want to take a look at the sign, not the actual number. So if this value is positive, which it should be, then I'm going to be concave up. I don't know why I didn't want to write my word up there. Now I'm going to pick a value between 0 and 2. So let's go with our favorite one. Remember plugging it into the second derivative there. We should get a down, or a negative number. And again, 3. I should get another positive one. So we're going to sketch this graph. I know, Miss Kimmy sketching graph. What? Oof, atrocious. So I've got a point at 0, 0. Too dark. And I've got a point at 2, negative 16. Too late. I'm going to put it there though, so you can see my 0, 0 point. So it's telling me from the left of 0, I'm going to be concave up. So I'm going to be curving upward. Between 0 and 2, I'm going to be curving downward. And then from 2 onward, we're going to be curving upward again. So this graph's a little funny. Now, it's kind of hard, not the best at drawing curves. If you want to make it a little more curvy, make it look a little bit more symmetrical, that would be A-okay. We all know Ms. Kim was in this for the number part, not the drawing part. Yeah, looks a little bit better. So that is my first example. Okay, so let's take a look at the second one. Oy vey, I got a quotient rule. Ah, scary, scary. Okay, first steps first. Let's take the first derivative. So I have low, d high, minus high, d low, all over low squared. So when I simplify this guy out, I get 2x. I get 2x cubed minus 8x minus 2x cubed minus 2x, which gives me a whopping negative 10x all over that denominator squared. And guess what, boys and girls? We get to do it all over again. Okay, second derivative now. I have low d high minus high d low. Chain rule going on. You could have, if you really wanted to, foiled the bottom out, but I really didn't want to. Now, before you start multiplying things out, hold the phone, because I want to point out something cool. What do you notice here? And here. And here. I have a factor of the denominator in each piece. Now, we haven't had any of these in any of our more simple examples. Because we weren't asked to solve or do anything else. We were just asked to go ahead and simplify it. But because I have a piece of each of these, what I can do is I can cancel this guy out. This will become a third. And this will no longer have an extra power out there. So what that does to my second derivative is it changes my numerator. So now I don't have to FOIL as many things out. So I have negative 10 x squared plus 40. Now, I have negative 10 times a negative 1, which gives me positive 10. So I have 10x times 2, which is 20x, times 2x, which is positive 40x squared. Excuse me. I almost forgot that squared. Simplify that down again. And I have 30x squared plus 40 over x squared minus 4 cubed. Now the next idea is to set this equal to 0 and solve for x. So when I set this equal to 0, I have a fraction. First steps first to get rid of a fraction is you multiply by the denominator. Now, over here my denominator cancels, and I'm left with 30x squared plus 40 is equal to, I have 0 times something, guys, which is just 0. Okay, cool. So that's solve for 0. Take out, the max I can take out is a 10. So I'm left with 3x squared plus 4 equals 0. Now when I try and set this guy equal to 0, and I move over that 4, I start getting into unpossible solutions, because then I'd get the square root of a negative number, which is what we don't want to do. So because this fails, oh man, I was doing so good. Because this fails, there's no point of concavity. So I don't know if it curves or anything. But what I can do is I can go back and use the first derivative and check that. No, you're probably saying I don't have enough room. Look at all the space you used. What the heck? Bear with me, though. Oh, man. Sorry, guys. So if I go back and use the first derivative, I kind of need the first derivative in my site, don't I? That's at this point here. So now I'm going to set this equal to 0. So kind of the same idea. Multiply by the bottom disappears. So I have negative 10x is equal to 0, so x is equal to 0. When I plug that in to my original function, I have 0 plus 1, which is 1. And I have 0 minus 4, which gives me 1 over negative 4, which is equal to negative 1/4. So my point is 0, negative 1/4. So here's my point. Now I need to see if I'm increasing or if I'm decreasing at this point. So from negative infinity is less than x is less than 0 to 0 is less than x is less than positive infinity. I'm going to plug this into my derivative here. If I plug in a number that is less than 0, so say I plug in negative 4, or negative 1, excuse me. So I'm plugging in negative 1. I get 10 over, that would give me negative 3, which is turned into 9, which gives me a positive number. So if it's positive, I'm increasing. If I plug in a value larger than 0, so say I plug in 1, I get negative 10 over 9, which would give me negative, which means that my function would be decreasing. And the sketch of this guy, if I'm at 0, negative 1/4, or give or take there, is just a parabola. So that's why this one doesn't have any points of concavity. It's a simple parabola. So I didn't know that it was going to... So it doesn't change. If I go back a second, it doesn't have that point of change or that point of flip, which essentially is what this looks like. There's no flip point. It continues kind of in the same path. So I know that one was a lot of work, and I'm sorry. But let's do this one. Alright, so first steps first. We have to take the derivative of it. So I'm gonna do it this way. I'm gonna call this f of x just because I like to keep my stuff neat. So I have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Which, if you notice, this whole first part goes to 0. So I get negative 12x over x squared plus 3 quantity squared. So now I need the second derivative. Oh, shoot. My cat is being annoying. So I have my low times the derivative of the top minus the top times the derivative of the bottom, so chain rule. All over the bottom squared. So to the fourth. Now this is the part where we jump with joy because we should see a factor of the bottom in all pieces. So this no longer is to the second power. This is no longer to the fourth power. And this no longer exists. Woo! So when I multiply this through, I get negative 12x squared minus 36. So I have negative 1 times negative 12x, which gives me a 12x. 12x times 2 is 24x, times 2x is 48x squared. All over the denominator to the third. Oops. Simplified up, negative 12 plus 48 gives me 36. So I'm going to go ahead and replace that. Come on. So I have 36x squared minus 36. So we get to set this bad boy equal to 0 now. What are you doing? When I multiply by the denominator, it ends up canceling out, so then I get 36x squared minus 36 equals 0. A couple different ways to solve this. You could factor, or you could just add it over. Either way. However you choose to solve this one, you should get your x values as plus or minus 1. So we're going to go way back to the beginning, and I'm going to plug in 1, and I'm going to plug in negative 1, way back into my function. So if I plug in 1 here, I have 1 squared, which is 1, so 4, so 6 over 4, which will reduce down to 3 over 2. And I'm going to plug in negative 1, which if we notice should give us exactly the same point. So now I'm going to take a look at my concavity. So I'm looking at negative 1, negative 1, 1, and 1. When I plug in a value smaller than 1 into my second derivative, which is right here, I should get a positive answer, so I should be going up. If I plug in my favorite value of 0, because 0 is between negative 1 and 1, I should get negative 36 over 9, which would be a negative number, so that's going to be down. And then same idea, if I plug in 1 again, since I've got squared stuff in there, I'm going to end up again. So, sketch-a-rooney this little graph. So negative 1 about up a third, 3 over 2, which is about 1.5. So we're going to say we're there, and we're going to say we're about there. Pretty fairly even, in my opinion. Again, this computer is not the easiest thing to graph on. So from the left side, we are concave up, so we're going to be curvy up. Between the 2 points, we're going to be curvy down. And on the other side, we're going to be curvy up. So there is my fun little wonky graph. Alright, that's all I got for you.